Dear students, we are looking at the memory module. In the memory module, we started off with the memory hierarchy. Post that, we have looked at caches in depth. We realized that there are multiple levels of caches in any typical system that we have. Post that, we have looked at the concept of virtual memory, wherein we got introduced to the page table, TLB, the concept of virtual page, physical page, and some implementation details of this page table and TLB. In this lecture and the next few lectures, we are going to look at the actual main memory and its controller. So because we already know about the virtual memory concept, whatever we are discussing now is the physical memory. So just a quick introduction, you can say, to the memory controller and the main memory. This was the typical motherboard we had until a decade back, wherein we had our CPU sitting here. It would be connected to a north bridge. The north bridge would be connected to the main memory. Also, it is connected to the south bridge. The south bridge is managing all the I/O. So a block diagram of the same thing. We have the core. The FSB connects to the north bridge chip, which can go to the graphics card also. It will be connected to the DRAM using the buses, and it connects to the south bridge using the DMI interface, and the south bridge in turn manages many other IO operations. So the serial ATA ports are typically used for our hard disk, and if you look at the BIOS flash memory, that's where your boot up of the system happens, and we and you're already aware of the many USB ports that we have. So this was the scenario until a decade back. What happened sometime from 2005-6 time is the north bridge was brought onto the chip. So Intel's Nehalem architecture, it had 4 cores, and we have the L3 cache which is shared across all the cores. And if you look at the periphery, you have a lot of IO and the memory controller. Almost in parallel, AMD's Fusion architecture was developed by AMD, and it too has the memory controller and some IO operations sitting on the processor core. Now, what is the advantage of getting the memory controller on chip, which is called integrated memory controller? We can pass more information from the processor to the memory controller, which will help us to do some better scheduling of the memory accesses at the memory controller. Also, it can help us to manage the memory better. In addition, it can also help us to manage the power consumption of this memory better based on the inputs we get from various cores. If it was off chip, to drive any of these extra informations, we would need an extra pin from the processor to the north bridge. But now we have more flexibility. The common memory hierarchy that we have seen so far, let's assume that we have 4 cores, core 0 to core 3. Each of these cores has a private L1 cache, instruction cache and data cache. They can be split or unified. Following that, there can be a second level of cache which is shared among few of these cores. Following that, we can have a L3 cache which is shared among all the cores. Any cache level that is shared among all the cores is called last level cache, LLC. and each of these cache has a corresponding cache controller. So if you look at the basic hardware of the cache, it is just the tag array and data array with some IO circuitry. But the control unit that actually does all the operations on it is the cache controller. Following the caches, we have the main memory, which is predominantly based on DRAM. We have its memory controller. Following that, we have the secondary memory and the disk controller. We'll now focus on the main memory and the memory controller. Now, if any one of you is wondering why should we study main memory, let's try to answer that question. Over the years, the technology at the core has improved dramatically. We have the concept of pipelining. Following the pipelining, it got expanded to out of order execution. We have much deeper pipelines now, and there can be multiple pipelines working in parallel, making a superscalar processor. Also, we can have many more execution units, fetch units, and decode units to improve the overall performance of the core. We can have a very complex and sophisticated branch prediction, which can almost eliminate all the control hazards. Over the years, designers have developed a very optimized instruction decoding logic. Also, at a little abstract level, there can be more than one thread running on the core. So it can be a coarse grained or fine grained or simultaneous multi-threading technology. Also, Intel has come up with a hyper threading technology. Basically, we don't want to keep the core idle at any given moment. Following that, we have multiple cores on a single chip. Even our mobile phones have 8 cores. Also, we can do overclocking on any of these cores. Overclocking means we can go over the regular standard specified speed or frequency and run it at a much higher frequency. Of course, there are some side effects of overclocking like increased power dissipation, so we need to do it in a controlled environment. But as such, if you want a improved performance for your core, at least for short amount of time, we can go for overclocking. In addition, we have a load store queue and highly optimized structure again. Just after the memory access stage, it will help us in reducing the number of stalls because of the loads and stores. And we have seen that following the code, there are multiple levels of caches. Each cache can have multiple ports. And we see that over the years, the size of caches has improved. In addition, there are many optimizations on caches to improve their performance. We have seen 6 of them. We have prefetching, we have miss status handling registers, so on and so forth. So the entire core and the cache on the chip have improved over the time. Now, if that is the case, why would I still need to look at the main memory? Aren't we getting the best performance that we can using the best possible core and caches? Let's try to answer that. Let's say we have a processor with a core running at 3.4 gigahertz and it has 3 levels of cache. Let's say L1 is 32 kilobyte in size and its access latency is 4 cycles and the hit rate is 95%. L2, let's say, is 512 kilobyte with 11 cycles miss penalty from L1 point of view and its hit rate say is 90%. L3 is 8 megabyte with 36 cycles of latency and let's say its hit rate is 65%. Following that, let's say we have our main memory and let's assume that all the requests to the main memory are hits, and it would take 80 nanoseconds for each access. With these values, if we quickly look at the AMAT for different configurations, let's consider for an ideal L1 where all the accesses in the L1 are hits. The AMAT would be 1.2 nanoseconds. If you consider L1 and ideal L2, AMAT increases to 1.3. If we have L1, L2 and ideal L3, AMAT further increases to 1.33 nanoseconds. And now if we have the entire memory hierarchy, which is a more practical view, the AMAT increases to 1.46 nanoseconds. Now, with the practical memory hierarchy, we can't override it. We are losing almost 17% in our AMAT, which can reflect in the worst case a 17% drop in the performance when compared to a single level of cache, which is ideal. Now to this, let's add multiple cores on the chip. The moment we say multiple cores, the L2 and L3 levels of cache will be shared across these cores. So the hit rate of these cores can drop drastically. In that case, what happens is many requests reach the main memory and experience the 80 nanoseconds time, which will eventually be reflected in at the pipeline as stalls and overall drop in the performance. Further, over the years, both the memory speed and the process speed have increased, but the rate at which the memory performance has increased is much slower than the process speed, and sometime around 2005 we moved from single core to multi-core. Till that point the memory's latency was an issue, but post that in the multi-core era we have the issue of the memory latency and memory bandwidth. I have already presented this figure at the beginning of the memory hierarchy. We call this the memory wall. Some more motivation on why we should study the main memory. Over the years, the nature or the characteristics of the applications we run has changed dramatically. The issues with the present day applications are they are very huge. For example, we have the big data applications. They are widely deployed in banking, communication, healthcare and insurance, education, manufacturing, government, trade, etc. Everywhere we have these big data applications which have huge memory footprint, which typically don't fit in our on-chip caches. What it means is the on-chip caches will have a lot more misses and we will end up coming to the main memory. Also, many of the current day applications don't have much locality. Now you know that the entire memory hierarchy is built on principle of locality, spatial and temporal, but the current applications don't have much of it. Examples are graph applications, which are predominantly used in social networks, our transportation networks, utility graphs, document link graph, and neural network. If you want a quick example of document link graphs, the way our web pages are arranged in the web on the web is a graph. Now, if we are trying to access one web page, there is no certainty that the very next page that we are going to access will be some X. It can be Y some other time. It can be some other new web page. The same with our social networks too. So these applications don't have much spatial locality. Also, the temporal locality might be very less. How often do we revisit the same web page? or how often the data in the same web page changes. If it is dynamic, it keeps changing very often. So where is the notion of the temporal locality here? It's very less. So for these applications, the on-chip caches, which are predominantly built to capture this temporal and spatial locality, have very limited scope. So we eventually end up coming to the main memory most of the time. In fact, for many of these applications, the main memory also needs to be very tailor-made, otherwise we'll end up going to the disk most of the time. Now with this motivation, let's dive into the main memory and its memory controller. I have given a couple of links you can go through. They are basically giving some examples of what the big data applications are, what graph applications mean, so on and so forth. It's just for the curious ones, not a compulsory read. Now let's say our the dotted box is our chip. We have the last level cache, typically L3. Following that, we have our memory controller. All the misses in LLC would come to the memory controller, and the memory controller has various jobs to do. The first one is address mapping. Following that, it will place the request into a transaction queue, which can be dedicated for reads and writes as RQ and WQ. Post that, each transaction is split into multiple commands and placed in one of these command queues. Following the command queues, we have the memory scheduler, which is managed by the controller. In addition, the memory controller needs to do few other maintenance jobs. Then it needs to manage the page table. Don't get confused with the page table we saw in the virtual memory. This is the physical page table. And it also needs to ensure timings for proper functioning of the DRAM. The memory controller is having two buses, address command bus and the data bus. The typical address and command bus frequencies are something like 800 megahertz, 933 megahertz to 1600 megahertz. Now we have even 2000 megahertz. Now the interesting point is the data bus frequency is twice the address bus frequency. It means for an address bus frequency of 1200 megahertz, the data bus frequency actually is 2400 megahertz. That is the reason we call our DRAM as DDR, double data rate DRAM. What it typically means is the data will be transmitted on the data bus on both the positive edge and the negative edge of the clock cycle. That's the way we ensure that the data bus frequency is twice the address bus frequency. Following that, we have our DRAM. Currently, it's a black box. If you look at how the DRAM is logically organized, we have channels. Each memory controller has a channel, and each channel has its own dedicated address and command bus and the data bus. And if we have multiple channels connected to our processor chip, all these channels can be accessed in parallel. There is complete parallelism. The channels are split into ranks. Typically 1 to 4 ranks are common. All these ranks share the address bus and the data bus. Now if you want to access two ranks back to back, then we need to space them out by TRTRS timing. We are going to look at it in the next few classes. TRTRS stands for rank to rank switching delay. Ranks are made up of banks. 8 to 16 banks are typical number per rank. All these banks now use this single address bus and data bus. and you can access two banks back to back in consecutive cycles based on the bus availability. Banks are further split into rows or pages. Here you can say that this is the DRAM page. So we have three different pages now: virtual page, physical page, and DRAM page. So at any given moment, we can access only one page in the bank. To open it, we need to send in an activate command. To close it, we need to send a precharge command. And to access the data, we need to send a cas command, column access strobe command. The typical sizes of these DRAM pages are somewhere between 4 KB, 4 kilobyte to 8 kilobyte. The rows are further split into columns. For every access to the bank using the cas command, one column of data is touched. It means that either one column of data is read or written to. Usually the column size is 64 bytes. And the time we need to transfer these 64 bytes on the data bus is T burst. We are going to look at it in next few classes. Let's continue our understanding of the logical organization of the DRAM bank. Let's say this is one row. We have few of these making our bank. At the end of these rows, to identify each of these rows, we need a row decoder. And at the end of these rows, we have what's called as row buffer. Now let's say we are sitting at the memory controller and we received a request 1 to row 0 and column 2. The memory controller will look at the bank and sees that the row buffer is empty. There is no page that is open in the row buffer. So we call it page empty. When it sees this, the memory controller issues an activate along with the row address on the address and command bus. The row decoder will decode this row and select one particular row, and all the data in this row or all the columns in this row are read into the row buffer. Following this, the memory controller now sends a cas command along with the column address, here column 2. Now that particular column is selected and sent out over the data bus. Now let's say the memory controller received another request 2, to the same row but maybe to the same column or different column. When the memory controller receives this request and observes the bank, it finds row 0 to be open in the row buffer already. So this is termed as page hit. Because the row is already open, we send a cas command along with the column address. That particular column is read out and sent over the data bus. Now let's say we received another request, but this time to some other row, for example row 10 here. Because the row which we want and the row that is open in the bank are different, we term this as page miss. When the memory controller sees a page miss, it needs to close the page first that is currently open in this bank. So it will send a precharge command. The precharge command basically writes the data from the row buffer to the actual row and decouples all the IO circuitry. Now at this point, the memory controller will send another activate with row address as row 10. Following that, it will send a cas with column address as 24, and eventually the data will be read out. So this is the working of a DRAM bank from the memory controller perspective. Now, occasionally we need to do what's called as refresh of these DRAM. When the time comes, the memory controller sends a refresh command to this DRAM bank. When the DRAM bank receives this command, the refresh controller, which is sitting along with the DRAM bank, gets activated, and it will issue sequence of activates and precharges. So basically what we are doing is we are reading row 0 to the row buffer and writing it back. The same thing can happen with row 1. We are sending an activate for row 1. We are reading the data to the row buffer and we are writing it back to that corresponding location. So this way, some predefined number of rows will be refreshed by the refresh controller whenever it receives the refresh command. So we have been using the term DRAM, that expands to dynamic random access memory, a lot. Let's try to understand that. A DRAM cell is made up of a capacitor grounded at one end. If the capacitor has some charge, we interpret that as if the DRAM cell is storing 1. If there is no charge in the capacitor, then we say that the cell is storing a 0. Now how do we access this DRAM cell? We have our dear NMOS transistor. Again, the gate terminal is our control terminal. One end of this NMOS, let's say the source terminal, is connected to the capacitor and the drain is the other end. If we want to, this drain terminal is connected to the sense amplifier, from where we read out the data. When we want to read the data, something called as charge sharing happens between the sense amplifier and the capacitor. So let's assume that the capacitor is storing 1. It means that it is holding some charge. So to read this cell, we apply high voltage to the NMOS gate so that the source and drain get connected and the charge flows from the capacitor to the sense amplifier. At this point, the sense amplifier drives it as 1 because it has seen some charge in the capacitor. If there was no charge, then sense amplifier will not see any charge and it will read out a 0. Now, as you have observed, the charge in this capacitor is no longer present. That is the reason DRAM cell read operation is destructive. It means the moment we try to read the capacitor, the charge in it gets disturbed, so we need to restore the value. That is the reason we send the precharge command. When we send a precharge command, the charge in the sense amplifier will be stored back into the capacitor. Now, why do we call this cell as dynamic? The primary reason is the capacitor, even if we are trying to access it or not, will lose the charge over time. So we need to do periodic charge refill, which is called as refresh. Now what we are doing as a refresh operation, we are accessing the cell, we are reading the charge in the capacitor to the sense amplifier, and we are writing it back, the activate and precharge commands. Okay, I have presented this device level detail just for giving an idea of how the DRAM cell is working. We haven't actually looked at more finer details. I'm not going to do that. Now let's try to zoom out a little. Let's say this is our DRAM cell, capacitor and transistor, and we have an array of such DRAM cells. The gate terminal of all these cells, which are in one row, are connected to a single wire. And let's say we have multiple such rows, and the drain terminals of these access transistors are now commonly connected to a single sense amplifier. The group of cells which are in one single row now form our page, and the common gate terminal, or sorry, the wire which is connected to all the gate terminals in the row is called the word line, and the wire that connects to all the drain terminals in the column is the bit line. Now the sense amplifiers, the group of these will form our row buffer. Now we have an array of these DRAM cells. We have a row decoder to identify one particular row, and at the end of these DRAM cells we have the row buffer. The row decoder will select one row. All the data will be read into the sense amplifiers, together called as row buffer, and now one of these some part of this data is read out using a column multiplexer. This is where we use the column address sent by the memory controller. It is important to note that the actual location of the row will not have any valid data because of the destructive read operation. So let's zoom out a little further. We have one array, and let's try to stack them in the third dimension. Then we have what's called as DRAM width. If we stack 4 such arrays, we call it as an export device. If we stack 8 such arrays, we call it as an X8 device. Many other device widths are possible from X16 to X72. Now what is the significance of this DRAM width? This width will determine the number of bits that can be read out from this group of DRAM arrays, or we can call it as DRAM device. Now if we have an X4 device, it means that each cycle this device will give us 4 bits of data. If we have an X72 device, then we can read out 72 bits of data in each cycle. Now with all the understanding of the DRAM cell and array and DRAM device, now let's come to the physical DRAM organization that we can actually see with our eyes now. Yes, the physical DRAMs are divided into channels just like what we have in the logical organization, but now channels are divided into multiple DIMMs, dual inline memory modules. Many of you would have already heard about this term. Each DIMM is specified by the CAS, ACT and pre latencies, and also the data bus frequency along with its capacity. DIMMs are now divided into multiple DRAM devices, and each DRAM device is made up of multiple DRAM arrays. Each DRAM device can itself be seen as a mini DRAM because the operation in one device is same across all the devices, and we specify the DRAM device with its width as X4 or X8, so on. The DRAM devices, when grouped, form what is called as a rank. Now how many of these DRAM devices form my rank? It is determined by the channel width and the device width. Device width we already saw, it can be 4 for an X4 device, 8 for an X8 device, so on. The channel width is the width of the data bus. If we say that the channel width is 64 and the device width is 8, it means that 8 such DRAM devices make my rank. Ranks are further divided into banks as rows and columns. We have already seen that. Now, if you are wondering how a DIMM would look like, many of you would have already seen it. This is how a typical DIMM would look like. Each of these chips is the DRAM device. Now, if you zoom into the description of this DIMM, we have few information. The first one is the capacity of this DIMM. Here it is 32 GB. Following that, we have 4R x4. It means that this DIMM is made up of 4 ranks, and x4 says that the ranks are made up with x4 devices. Following that, we have a number 2133, which is the DIMM frequency, specifically the data bus frequency 2133 megahertz. So there are many variations of DIMMs that are available. I have given a link. Not that I am endorsing Samsung here. I found that the link to be very useful, very informative. For the curious ones, they can go through it. There are many different aspect ratios of these DIMMs. This is the DIMM we have seen, and that is what is typically used in our desktop systems and workstations. For laptops and tablets, the DIMM size is smaller. And if you're wondering how the DRAM would look like on your mobile, it looks something like this. We can have a single or maybe two chips, each of capacity of 2 GB or 4 GB. Together, they're giving us the total capacity in our mobile phone. So with that, I'll pause this lecture. We'll continue looking at the DRAM and the memory controller throughout this week. I'll pause for now. Thank you.